Okay, so welcome everybody to our second mentorship session for the 2023 Building AM Design Competition. A couple housekeeping items here at the beginning. First off, next week, same time, what we did realize is you do have to click the new registration link. So make sure you do that. But same time, we will be doing Design for Additive Manufacturing Basics. That mentorship session will be done by Haley Fox, who is an additive manufacturing engineer at EOS. Today we're going to be talking. Oh, if you missed last week's session and if you missed this week's session, all of the sessions will be posted to our website as YouTube videos. So feel free to go back and review those at your leisure. We would encourage you to be here in person at the sessions, as you'll be able to ask questions at the end and maybe get a leg up on everybody else. Today we're going to be talking a lot about ANSYS Discovery. There is a free student version of ANSYS Discovery that is available. If you go on our webpage on the competition website and go down to the judging criteria, you'll find the section stiffness to weight ratio. In that section, there is a link to where you can download ANSYS Discovery. And that's all I've got. So today we have our mentorship session is on topology optimization basics using ANSYS Discovery. Jorge Plumareyes is an applications engineer at ANSYS, and he has some stuff prepared to show you guys. Over to you, Jorge.
Cool, thanks. Let me go ahead and open up a session here. And the understanding is that I'll just start from scratch so that I assume that there's no real knowledge in discovery. So let me do that here. Let me open the model. Okay. And let me share. Can you guys see the window?
Yes.
Perfect. So let me just kind of start from the top. You guys are gonna get a kind of my spiel of discovery as presented to customers. So I'll give you like pretty much a real professional view of how we're um, setting up discovery and how it's to be introduced not only in your guys's project, but just generally in the industry and how it's being positioned and leveraged. So I can go ahead and start here right from our welcome screen. If you guys haven't been too hands-on with simulation tools, it might be you might have not have the experience of seeing how difficult they can be, right? If you're using like, for example, ANSYS Mechanical, which is an amazing tool, but it can be very difficult to manage, especially if, you know, with all the technical jargon, right? Elements, nodes, nonlinearity, all those things that make analysis very complicated. With discovery, the idea is that a lot of that complexity is removed and it's also simplified to in a way where you don't have to be an expert to use it. It does a lot of automation in the back end so that you can just have a great user experience and complete your project. Obviously, with this software not being on par with like very physics focused items such as fluent or mechanical and ANSYS, you are not going to get that 100% fidelity, right? But the idea is that this is going to be a directional tool so that you can start and go moving along the right path as you mature your design. So that's a real quick spiel of what discovery is. Now, here right away when you open discovery, I think this is going to be very useful for you, especially having used the tool. We have a very great user interface starting with the welcome screen. There's, you know, once you start using it, if you get student editions, you'll see new things that get included in discovery, which is very beneficial if you're kind of tracking that information. But right away, you know, you get a lot of hints on how to do discovery, how to manage it, how to maneuver around it. I believe with the student version, you only get model and explore. I'll have to double check on that, but basically the way it works is that if you're in model stage, you do a lot of geometry edits. You are able to do all of that in this stage. When you enter the explore stage, that's when you get to leverage the physics aspect of discovery, which is probably the most powerful thing here. And from there, you can use the refine, which kind of uses the flagship products that ANSYS has, the mechanical fluent. So it's more higher fidelity, right? But it's and again, I'm not sure if that's included in the academic version. I'll have to double check on that. But we'll pretty much be focusing on the explore stage, which is pretty much the bread and butter here in discovery. And again, right here, a lot of useful information on how to interface with the software and a lot of navigation tips and tricks. And something that's very key here in discovery that you'll be able to kind of maneuver as you get yourself situated with the software and starting to put your geometry in here, or maybe creating it in here, is that we have an interactive help menu, which is very unique to discovery. I believe it's being patented, but I could be wrong. That's what I've heard. But pretty much what it does is that it kind of guides you through the process, right? Especially if you're new to this. And I think that's very beneficial if you're starting off with the analysis world. So I'll kind of touch on that here in a bit too, but that's pretty much a quick overview of what discovery is and how you can get started. From here, we do have an interactive tour based on what you want. You can see here that we have a topology optimization one, which honestly is so great that you might kind of just ignore this video in the future and refer to this, but I'll try to match the quality of this tutorial here, but very useful if you want to see how to set up a problem or maybe do other types of things here in Discovery. And from here, we have sample problems. So in addition to those tutorials, we have problems already set up so that you can kind of see how the setup was done, see how it kind of compares to your problem, how you should, the do's and don'ts, right, of the setup so that you can apply it to your problem and make sure that you're getting the best results for you. Here you'll see that we have the bracket topology optimization, which will probably be something you guys open up and kind of see in addition to all the other feedback I'll give you here in this session. So for our case, I already have a bracket loaded up. So a couple of things here. Something that's very unique here in Discovery, as opposed to many of the traditional CAD softwares, is that we're feature-based modeling, which means that we're not tied to, let's say, a sketch when trying to make updates, which is something that's very, very useful if you're trying to do real quick changes, kind of explore your ideas and put them not onto paper. In this case, it would be onto Discovery, but that's pretty much the idea. So for example, if I wanted to, let's say, take that in here and take this in here and just kind of wanted to move them a bit, I can do so freely. Let me update this orientation here. So yeah, you see how traditionally doing things like this in a more conventional sketch kind of way can be very difficult, but and maybe not difficult, right? But a bit longer than usual. So here with Discovery, you really can do a lot of changes at once and are able to leverage things in a way that will be easier for you and will be advantageous to the whole part. So I can, for example, select this whole face. Maybe I want to pivot about this edge here. I can go ahead and just do that rotation. If perhaps I want to bring this guy along for the ride, I can kind of do that here, right? So very, very cool things that, again, is unique to feature-based modeling, such as here in Discovery. So that'll allow you to really be a bit more faster with your modeling here. And yeah, so that's pretty much the geometry side of it, right? How it differentiates itself from a lot of traditional CADs. So from here, let's go ahead and do what we are probably here for, which is the physics portion of it, right? So the cool thing here with Discovery is that, again, right, easy to use. So here's the interactive help menu, which you can access here by clicking F1 or going here on this upper right corner. So from here, you can pretty much navigate or get navigated on how to set up the problem. So for example, right, like if I want to set up a structural problem, I go to my simulations tab, click on structural, and you'll see as I move forward, the software guides you towards what you want. So in my case, we want to set up this mechanical problem, right? So we know that we're gonna need to have constraints and have a load. So setting our boundary conditions. Here, I want to have a fixed constraint. So what I can do is go to my supports here, and then it literally just adjusts to where you're going and kind of gets tailored to what you're doing, right? So here it tells you what to do. I would, for example, here select my appropriate faces to constrain, and just like that, right? I have my constraint selected, and I just click accept. Also, I'd like to know that we have videos here, right? People typically say pictures are worth 1,000 words. So with Discovery, these videos really do are advantageous because I recall my university days where I was look something up, not know how to do it, go to the manual, maybe not, then go to YouTube, right? And eventually end up with those solutions. So the attempt here is that a lot of this is self-contained so that you can continue learning through Discovery without all those third parties, which are available to you. We do have a lot of support online as well, but the idea is that would be minimized if possible to help your process. So from here, I just click accept, and you can see I have a lot of different types of boundary conditions here. I have moments, displacements, forces, pressures, and so on. My next thing I want to do is put a load here. So I'll go ahead and click on my force, and I'll do a distributed force, click on my face here, and I want to do a components, see? And you can kind of see, right, how everything just keeps on getting adapted to what you're doing and what step you are. In my case, I'll do a load of 500 newtons, and I'm pretty much set up. I'll go ahead and exit out of this interactive menu, but it's important to know that it's always there because it will help you along your process, whether you're doing structural problem, fluids problem, thermal problem, topology optimization, whatever it is, it's very useful and advantageous to be incorporated into your process if you get a little stuck or maybe you just want a refresher on something. So from here, I'm pretty much set up. So this obviously this is a simpler part, right? It's kind of just a bracket. If you were to have a more complicated geometry, the steps might be a bit longer, maybe a little bit more detailed, but the idea is that this is it, right? You just assign boundary conditions and you can go ahead and click solve. And I'll do that here on my right, and that'll be my solve button here. So here, you can see the contour plot already, right? And that's the key here in Discovery. We have a proprietary GPU solver which does simulations live. So you guys probably heard stories, right, where engineers in the workplace, right, they set up the problems, click solve, then they go home, right? And then the software takes hours to run, and then sometimes if you hit a snag, you have to do it all over again. So that's hours and hours and hours. So the idea here with Discovery is that we bypass that. Of course, in that manner, like I mentioned earlier, you do sacrifice a bit of that accuracy and fidelity, but for initial stages, it is completely fine to kind of sacrifice that for that speed and real exploration that Discovery gives you as you maneuver through your problem. So in this case, we have our solutions here already. You can see we have our contour plots, our deflections, similar to any physics software out there in comparison to Discovery, like mechanical, for example, within ANSYS. We have our stresses and various other things that are useful to use. So another key thing here, prior to your topology optimization, right, when you're doing that stiffness to weight ratio, you might have different problems, right? Maybe you want to minimize stress, maybe you want to minimize displacement. It kind of just depends on what your problem is. So I'll give this example of displacement, right? So let's say I wanted to reduce the amount this bracket is being displaced. So what I can do is pop over here to my monitors. You'll see that I have by default factor of safety, maximum displacement, and maximum easy stress. We can create more if needed. We can select a phase, the whole parts. By default, this is done, the default values are for the whole part, but maybe you're interested in only one part of an assembly. Here we only have one part, so it doesn't apply, but maybe you are interested with a surface, edge, or whatever it may be, right? So that was the idea there. For us, we'll just choose the whole part and use these default monitors here. So we see here we have our maximum displacement, and let's pop open that stress one as well, just kind of see how it changes as we make some modifications. So let's say, hey, we want to reduce the displacement. Our design's going good, but this part is affecting a bit too much. So what we can do here is take this guy and see how we can reduce that displacement, right? Some pretty common things to maybe do is just kind of make this hole smaller, right? So in our design tab, there's a lot of different tools, but I would say pull and move and fill are probably the key components you want to be working with, the key tools. So if I select my pull, for example, or control P, sorry, not even control, just select clicking on P, I can kind of make this smaller, bigger, how I kind of wish, right? So if I make this smaller, I expect my displacement to get smaller as well, since we are adding material. And you can see, right, pretty quick, this already solved, and you already have this feedback here in Discovery. So I see that my displacement went down, my stress went down, so we're good on this problem, right? We are kind of doing what we tried to do. Maybe for some reason, you're tasked with updating the cutouts, right? Maybe the orientations are no longer valid. What you can do is take this cutout, move it over here, maybe give it a quick little rotation as well, and then kind of see where that leaves you. Maybe I'll do a whole 180 or 181 and kind of see where that leaves us. And that's the key thing here in Discovery, right? If you, whoops, I moved that a bit too much over here. But that's the idea here in Discovery, right? If you are working with a this Discovery software in which you can do all of this live, it's very beneficial because you're basically shaving off hours, if not days, right? Depending on your problem, the complexity. And this is very advantageous because you can see that I'm doing all these changes and that I'm able to get results right away. So this is kind of how you would use Discovery. This is how you would guide your design, right? And the idea, I think, for your competition was that stiffness to weight ratio. So these are definitely preliminary steps, right? Kind of like that probably mechanics and material classes, right? Your cantilever beam, seeing some initial preliminary sizing studies, right? So this is how you would use Discovery in your initial stages. So from here, another thing I can show really quickly, I can't recall in detail all of the judging criteria, but if you were to also want in the mechanical domain in simulation, we are also able to give you natural frequency. Again, I don't recall if I saw that, but I'll still touch up on here because I mean, if you're dealing with rotating things, if you have that vibration aspect of your problem, then that's something you definitely account for. Whether or not you need it, how quickly show it here. And it's pretty quickly here solving that. Let me see here. Turn on the deflections. Probably, if you guys recall from your classes, right? We have our mode 1, mode 2, mode 3, so you'll be able to track that here. And similar to our previous problem, if we were to want to make some changes, we can track the frequency. Maybe we want to increase it. We can select this space, for example. Let's say we click on our P for the pull tool. This time I can click on my edge so that I can make a copy of it. Let's go ahead and bring it down here. And then what I can do from here is pull this guy out, kind of give me a little overhanging rib or some structural support here that would maybe increase that frequency as it did right here, right? So a lot of cool things that you can do here with Discovery. Let me see. I'll make sure I can monitor the chat in case if there's any questions coming along. But yeah, I think that's pretty much the introduction to Discovery, right? How it can be used and leveraged and utilized to your advantage here. And from here, I believe, and go ahead, correct me if I'm wrong, Gary. I can bypass the fluid thermal sections, right, and jump straight to topology. I don't think there's aspects of that in
Correct.
in your challenge. Perfect.
Correct.
Cool. Yeah. So let me go ahead and do that then. So with topology optimization, let me go ahead and open. I'll go ahead and open a different model to kind of get a good idea here of the process here in Discovery. So I have some fully set up because the topology of this optimization does take a bit longer. So I will do that here. I have something kind of pre-solved to show the idea of what topology optimization would be doing here, right? So again, simple problem. Everything will be, I feel like it's kind of like when you're in school, right? You're the teacher is going over something simple and then they task you to do the impossible back home. So hopefully it doesn't seem this way here, but we'll touch these simple problems only because it's kind of quicker and easier to visualize. But let's say we had this problem, all right? We have this base here and we have this cylinder here. So if we wanted to have this problem where we have this fixed bottom and we have this force coming in this direction, we can go ahead and model an instance like that. So what I would do in this problem is, let's say I want to add an enclosure to kind of give this part some reinforcement, right? So let me pop that idea up. So you see this outlining material is transparent, but it's pretty much a solid, right? So that would be my enclosure. So let me make it transparent again. And the idea is that I want to obviously not use this because this would give me the maximum stiffness, maximum reduction in stress, right? We have this big piece of aluminum just encasing our whole problem. The problem is that often that's not the ideal approach because you're just adding a chunk of material, and the idea is to try to make this lightweight while still serving the purpose of reinforcement, right? So if I bring by my cylinder and base, I can visualize the problem again. So here, like I mentioned, it's already pre-solved only because it does take a while. But here in simulation, what you would do is click on topology optimization and select the part that you're trying to optimize. So in this case, I have my enclosure, so I'll hide my other two. And I have a distributed force here on the top, and I have a fixed support here at the bottom. So when I click on topology optimization, this window pops up. And there's a couple of options here. So first thing is you get to choose your approach, right? So in this case, we have the ability to choose how we want to optimize, whether it be to maximize stiffness, maximize natural frequency, maybe we have a target natural frequency, we want to minimize volume, minimize stress, and so on, right? You have the ability to choose your approach while the solver kind of eats away at your material to optimize your body. Here, the second option is, oh, sorry, the second input is to put in your reduction value, whether it be a percentage or an actual volume number. You can answer that here, and it'll do the reduction by that percentage in this case.
Or hey, it looks like we might have lost your screen.
Oh, see here. Okay.
Jordan, are you able to see his screen still?
Let's see what Jordan says. Oh, interesting. Let me see. Let me stop sharing and share again, see if that helps. Is it back
Okay.
on?
Now we
Okay.
can see it. I think we lost it right about the time you loaded this file in.
Oh, shoot. Okay. Oh, okay.
Sorry,
Let me.
I jumped out of the meeting and hopped back in to see if it was just my connection.
No, you're good. Let me do a quick recap here, which I think the the main thing is the topology optimization icon. So again, right, really quick overview of the problem is that we have this base, this cylinder. We want to fix the bottom and add a lateral load here on the top. So and, and that's the problem setup, but we want to kind of surround this with an enclosure that will reinforce it. However, we don't want to add this whole big chunk of material, right? So we don't want to just blast it with a kind of blocks and cylinders of aluminum. So the mission here is going to be or the goal is to do some topology optimization to reduce the volume and weight of this. So a quick overview of what I was showing earlier was the topology optimization option in the simulation tab. Once you click that, it turns your problem into a topology optimization problem. And of course, you still have to have your boundary conditions set, so your force and your fixed support in this case. And when you click on that topology optimization, you have to choose your topology optimization approach, whether it be to maximize stiffness, which is probably what you guys are going to choose, minimize volume, minimize stress, maximize natural frequency. We have various options here. But again, I think maximizing stiffness will probably be something that you will be selecting here. So we'll go with that. And then you enter the volume reduction, right? Do you want to reduce it by 20%, 50%, right? Even though you are optimizing your stresses, your deflections, all those things will reduce, and just because it's the nature of the problem, right? You're removing materials, so it's going to happen. But the idea is that it's happening by a very, very small amount because it's an optimization problem. So you have to kind of see where you want to lie in this volume reduction value. And another key thing here is to the protective depth. Pretty much any protected region here you see will be where the constraints are. So here I have my force, therefore I'm going to protect this upper region, and I have this force here, which is going to this support here, which is going to protect this bottom part. And when I say protect, I mean it's not going to get material removal in the process. So if I click solve, it starts to chew away at material. Again, I'm not going to click it in this case because unlike our previous problems, this one actually does take a bit longer. So it's better to have it here preloaded. But pretty much what happens is when you click solve, you'll see the material start to kind of like, or discovery start to chew away at the material that would be considered excess in your approach. So the resulting the results from that would be this in this case. So let me go ahead and show you what you would see. This is the facets body that would be produced through this topology optimization. So in my case, I had a distributed force, and I was able to kind of give a couple of parameters. So if you want to optimize your body for certain load cases, you'll have to in this case, go to distributed force and make sure I click on add as a parameter here. And what that does is it pops up in this window, which then parameters you can assign them, right? Whether it be you want force of magnitude. In my case, I said components because it's better to work with. And then I added all my test cases. So I did a load in the X, a load in the Y, and a load in the Z to kind of give me that balance in each direction. So that the result of having this problem set up and having this geometry resulted in this optimized body, right? And again, this is going to be giving me probably larger deflections, larger stresses than would this solid part. But the idea is that um, it's still advantageous. So I'm still meeting my deflection limits, my stiffness, my stresses, everything is still within tolerance. So I'm able to use this optimized body. And what you can do from here is, depending on your next steps, you can create a smooth facets version, which is pretty much what it sounds like, right? It's a smoother version of it that is typically used and preferred for manufacturing purposes. So you see that body here. And you can also create a solid from it, which would be this example here, and it'll just be a solid part that you can modify with surfaces here. And the third and probably coolest feature here in Discovery is that you can convert it into a sub-D model. You would just click on your facets body and go to our sub-D tab and click on convert. From here, you end up with this subdimensional model, which is very I like to say gummy, right? Because I'll show you here in a bit. It's very organic, and you can kind of mess with it a bit. So let me hide my cylinder and base, so I can give you an example of what I'm saying. And by the way, you can also make simulations on these parts as well. So let me hop over to a different tab in which I kind of already set this up. So here we have the same shape, right? So we have our force on top and our fixed support on the bottom. So from here, I would be able to see the results on this body. So similar to the other parts that I had originally, I can see the effects of this here. And again, this would be a resulting body after topology optimization. So here I can see my deflections, and I'm able to kind of visualize how it's acting. I can see my stresses and so on, right? So I can do all that here. And similar to our previous problem, if I wanted to do some changes, I can do so as well. So I could take this view here, maybe click on my design tab, go to pull. Maybe I want to, or maybe move. Let's go ahead and just move all of this portion here. I can drag it up, make it taller, which is something that you could probably do with the with just a regular body, right? That's not something too complex here. So here you'll see that it pulled up and the GPU solver is kicking up in the background to start the new results for that. Similar to our previous problem, you'll also be able to kind of see all of the different values here, right? So I'll just leave this one open up here so we can track it as we make various changes. If you see that your optimized body is lacking in some instances, you can do some really cool changes. So here, for example, in the sub-D tab, you can, well, let's go back to the design tab. You can, aside from that move option, right, you can do a variety of different things. So maybe I want to take these spaces here, and let's just say I want to make them a little bit bigger, a little bit bulkier. I can kind of thicken that part up. And then again, right, I'll get my results live here, but you can see the effects of kind of just grabbing some sub-D elements here and kind of just making this chunkier here. And you'll see that the part is acting accordingly. Here we see that we have some high stresses. What we can do here is go to our sub-D tab. Maybe we want to do some cool editing here, so we can grab on maybe two faces here, and let's do the same thing here. Maybe this one face here, and we can go to bridge, and it'll kind of give us a bridge between those links. So I can click on OK, and then I can kind of see what the effects would be of adding that portion there, right? And again, this is a very special, unique problem that might not be applicable to you. But the idea is that after you optimize, you're able to see very similar features here. So quick kind of idea of what you can do here in Discovery after optimizing your body. Maybe I want to make this a little thicker too. I can do that. And again, right, you'll be able to see all of this live. As you make changes, you'll be able to monitor the change, the displacement here, for example, and you'll be able to do all that here. So very, very cool stuff. And again, I think it's much cooler when you actually do it on a problem. So I think I'll hop over to that next. If there's no questions, I believe there isn't, at least what I'm looking at. So I'll move on to kind of tying all of this together, right? So we took a look at what Discovery does, which is giving you the ability to do really quick live updates to your geometry and being able to visualize it both through results and physically as you make changes. And I think this is key, right? Sometimes as engineers, we have all these brilliant ideas and it's difficult to definitively say what it would do because often the way we do this, at least at school or sometimes even in the workplace, right? We kind of idealize problems with cantilever beams and so on, right? But very conservative approaches, which often, like my previous lead, you just say at some point you get so conservative that you're just wrong. So the idea here is that you're able to take all of these changes, put them in Discovery, explore your ideas, and be able to visualize those results and see what they are doing to your overall problem. So
Okay, one quick question for you that I'm
yeah.
sure at least some people are asking in their minds. What if you make a change to your sub D model that makes it worse? Is there a way, aside from like Control Z, to go back to the state you were in before?
Yes, that is a very good question. And I think that my answer is Control Z for now. Yeah. I think as when it comes to your sub D model, there is options with more a traditional body, right? A traditional solid. But with sub D models, given the nature of the body, I believe that you kind of do have to be a little careful there and do a little bit of Control Z. But that is a good question. At least the way I've seen it is that, yeah, I'm taking a note to myself to follow up on this. But the way I've seen it is that you do have to be a little careful with that Control Z, because since this is more of organic body, you can't really look at it from a phase or a circle and like a parameter, right? It's a little more tricky. So I'll definitely follow up on that in case there's a trick I don't know of. But I think the answer is just being careful with your changes and tracking the 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 Control Z and kind of using that to your advantage. One thing we do have, which might not be exactly what we're looking for in this case, but we do have scenes where you can kind of save your results, right? And you can, in the end, make a report here, create a report that will kind of pretty much take all your scenes and visuals and results, everything, and give you an idea of how your change or how your results change. But yeah, you wouldn't be able to see exactly which element, how it was oriented, how what position it was in. So that's a little bit of a loss there. But yeah, I would say just be a little mindful while doing all these changes with sub-D modeling.
Yeah.
Cool. So anyway, if I do hear otherwise from my team here, I'll shoot out an email too, so you guys can share. But yeah, cool. So I think from here, I'll do a quick showcase of a real problem, right? So we connected that with with our initial design changes. So now we have topology optimization, and let me go ahead and open up a more relatable example here. Cool. Oh yeah, sorry, I'm looking at the messages now. That other thing that looked like a joystick. Okay, so here we have a more like I was saying, right? We were looking at these simple parts, but here we have a more complex quadcopter, for example, right? We have
It looks
the
like the screen froze again, Jorge. Might have to
oh, okay,
unshare and reshare again.
yeah, let me do that. Unshare. Can you guys see this?
Yep, we can see it now.
Okay, cool. Yeah, thanks. Go ahead and feel free to interrupt me if I'm no longer showing something. Um, but yeah, here we have this obviously more complex geometry, right? We actually have an assembly of parts which create this quadcopter as opposed to a simple bracket or that little joysticks simpleness, simple pieces of blocks and cylinders here. So if you have your design made already, right? Whether it be done through I don't know, SolidWorks, whatever you're using, Creo, the Discovery is CAD agnostic, so it will take in all of your previous CAD files, and you'll be able to modify them. So don't be afraid if you are like um, dedicated to Creo, for example, or Inventor or whatever it be, you can transfer it over to Discovery with minimal issues. We do have these repair and prepare tabs, which really do capture a lot of the typical issues in CAD uh, transfers. So you should be pretty much good to go from there. And if not, I think these tools will pretty much get you there in anyways. So from here, we have this problem, right? So here I kind of set up some things already. So what I did was assign my materials. So I think I didn't mention that, but in the simulation tab, you can assign materials. So you just click on your part and then just click on materials or click on materials, then click on your part and give it whatever material you choose. I have an extended version, but the local library is still pretty well, pretty well stacked. So for example, you'll be able to see brass, bronze, laminates, plastics, and so on. But yeah, this is already pre-designed with materials. We have a simpler model here. So let me go ahead and what I did for this problem, I kind of focused on the wings first. So if I hide everything else, kind of just to be able to focus on the wings, and you do that through selecting, right? Selecting, making some groups here in your tree. I can go ahead and hide everything that I'm not including in the simulation. So here I have my wings, right? So similar to the previous problem, I put my load, which would be here, right? Where um, the rotor assemblies would be mounted. And I put a fixed support here where I would be expected to be attached to the main body. So from there, I can go ahead and start the simulation process, right? Something to note that there is a lot of context here, right? So you have your bolts and whatnot, and the extra parts touching each other. So by default, Discovery automatically detects all of these contacts and it makes them bonded contacts. But you can go in and modify them, right? So for example, in my case, I wanted to say or idealize my bolt to be actually bonded to these parts, which they're not actually bonded, but with a tight fit, it's not a crazy idealization here. And I kind of just updated my condition here from bonded between my two parts to sliding. So this is all you can do when you open this. By default, everything is bonded, but you can go ahead and select specific parts and make them sliding parts. Maybe you have a joints or you want to permanently bond them, or maybe just ignore them. That's up to you and how you want to set up your problem. But from here, the process is pretty similar, right? I set that up, I click on solve, and then it's good to go here. I can see my results and I can see my visualizations here as well, which would be pretty much similar to what I expected here, right? So that would be this problem with a bit more details in it. And here, once you solve it, maybe you made some geometric changes and you're kind of ready to see how it would look optimized. I did that here as well. So I go to my optimization solution here. And what I did was I just wanted to optimize that top part, right? I wanted to see how it would look if I took this and just made a topology optimization. So what I did was I clicked on that part. I said, let's maximize stiffness and let's go ahead and reduce the volume by 50%. And let's make sure that the constraints where the load goes here and where we're constraining to the body are protected. Let's make sure that those bolts are still good. And let's make sure that any areas that get attached are good. So I did that by default. Sorry, that was done by default, plus some additional ones done by me. And from here, the same problem, right? You just kind of have that force up and some fixed supports here. The result of this, after clicking on solve, was seeing this guy here. So I started off with my facets body, right? The part that we kind of saw earlier. So we went from that first wing to this. And again, I can make my a smoother version if I wanted to here. And that sub D version as well, which I can make some additional modifications to. So this was kind of the result of me saying I want to reduce 50% and I want to maximize stiffness. And keep in mind, this can be considered both as an end product or directional, right? So some of these things might look a little wonky, right? But it really does give you insight into what parts are essential for you to maximize that stiffness as you reduce your volume, which I think is key. The key thing here, right? You'll get an idea of what you have to kind of protect in order to optimize your stiffness to weight ratio in this case. But yeah, that was this problem, and I'll give a quick example of what's something you guys will be doing, which is the chassis. So let me go ahead and hide all suppressed. And this is that center body, right? So here, similarly, I put some gravitational loads. I fixed my locations where the wings would go, and I'm letting this body kind of just go up and down. And I modified my contacts. And I think, again, this is the part where you guys probably will be working with something more in this realm here. And here I can see my results again, right? This is, you can see my oh, by the way, these are exaggerated, right? If you click twice, it gives you the more realistic deformation, which is kind of hard to see because it's not really that much, but it's useful to see the exaggeration to get an idea of how things are moving. But you see the sliding there and you see my chassis in the inside. And I did a similar thing here where I did a topology optimization of the top lid, just for example, and it ended up with this product here. So I took this top lid that was on the quadcopter and I did some optimization on it, and it gave me this fastest body here. And again, you can create that smooth version and ultimately create your subdimensional model for some on the fly changes here if you wish. And again, right, this is just directional or it can be an end product. A tip I do have for you if you use it is to take your original geometry here, for example, and it's similar to what I did with that cylinder, right? So let me bring it back in really quick. Actually, I can go to previews. Recents. Let me open this guy up again. And yeah, and I'll end with this tip, but pretty much what you can do is if I wanted to optimize this body, for example, let's say this was the body, I wouldn't start from here if I have the chance to add more material. So what I would do is kind of create a bigger chunk of material and allow the software to have more material to chew on and kind of eat away optimize your body, because if you give it
Could you
your
refresh your screen share one more time? Looks like
oh
anytime
yeah,
you open a new project, it does that.
interesting, good to know. But yeah, I'm just bringing up that old project, right? So if I had this, for example, my this simple block and cylinder here, and I wanted to optimize it, I might want to maybe increase this by, I don't know, a bit here. And I would want to do the same thing to my other faces. Maybe pull them up a bit. Why? Because even though these aren't the dimensions I want, it'll give the discovery more material to chew at, and it gives it um, more material to kind of run through as it's optimizing for your solution. So kind of just a quick tip on that, but I think that pretty much covers it. I don't know if you guys had any questions or any follow-up things you'd like to see. I think the time is pretty much
Oh,
closing up here.
that was really great. Very technical, and it was really good. I enjoyed it. I'm gonna go ahead and pause the recording, and then we'll let any questions be asked here. So,